Well, in this video, I want to talk about the usefulness of the normal distribution. The normal distribution does occur naturally in a lot of systems. There are a lot of things out there that are stochastic or systems with variability where there's a middle that happens most often, but it doesn't happen all the time, and the chances of missing that are spread out, and it looks like a bell-shaped curve where you can miss. You can be high or low, and often it's equally. So when there's a lot of things that are unimodal that have one hump and with symmetrical tails on the end, just occurring naturally. However, there's other reasons, and there is something that we rely on in inferential stats called the central limit theorem, and the result of that is because of you'll see the normal distribution shows up when we do things, when we start doing sampling and calculating statistics. And I'm going to show you what I mean by that. So I've got a worksheet over there called the central limit theorem that I've set up. And what I've done is I've rolled dice. And if you notice what I've done, I'll zoom way in. I've rolled a dice, and all I did was use an Excel function called ran between, and all it does is give me a number equally likely between 1 and 6. And if I did that a whole bunch of times, 1,000 times, and then I plotted the frequencies of those, and this is what we get. So the chances are the outcomes of 1 was 170, and I could redo it. But if you can see, when you plot that, you get something that looks like this, which is what we would expect. It's a uniform distribution. The number of 4s is approximately equal to the number that we get 3s. And we could rerun this to get a different one, and we could run it again and run another 1,000 and another 1,000. And all I want to show you is that although they're bouncing around high and lows because of variability, we do have this uniform distribution. Keep in mind, we don't always know what the underlying distribution is. That's a challenge in other systems besides dice rolling. When you're doing manufacturing, or you're timing something, or you're plotting the life of something when it fails. And it's not always do you know what the underlying distribution looks like. But what if we take a sample? Let's start taking some of these dice, and let's take a sample of these. So I'm randomly going to grab 10, and rather than focusing on those particular 10, I look at the average. I'm going to take a sample and take the average. And I've done it over here to the right. So I've got different ways, and I'm not going to get into the formula, but I'm grabbing from those dice rolling. I'm grabbing from those, and I've done it up to 25 times. But more importantly, if you look over here in these last two columns, this column is an average. If I took a sample of size 10, I grabbed 10 of those, and I calculated the average. And this one, I'm grabbing 25 and taking the average. So now that I've taken the averages, I'm not going to worry about the actual individual samples. Let's just look and think about the averages. So here are the averages. Now, I had to do it a whole bunch of times so we could draw pictures, but what do you think the shape, if I would plot a frequency diagram of these averages, what do you think they would look like? Do you think they're going to look like this, just a different version, or what? And I'm hoping that you'll have some intuition and be able to see that if we would plot these averages on a histogram or frequency diagram, we're going to see something like this. And if you focus on the blue first, that is when the sample size is a fairly small, or a sample of size 10. But even with that, notice what happens. We start getting a distribution that starts to look like a normal distribution. It's larger in the middle, and it has tails that are symmetrical on both sides. And when we take a sample of larger than 10, you also get the normal distribution where we have a larger middle and our tails aren't out as far. Now, what's great about this isn't a trick where it only works for dice examples. regardless of the underlying distribution of this. Whatever it is, I know that if I take samples and look at the averages, I know that the averages are going to be distributed normally. They are going to look normal, and there's formulas that tell me exactly what the mean's going to be and how much variability, how much area in the tails. I can take advantage of that when I'm trying to determine if my process has changed or if it's changed or not changed. And I can lean on the fact that the average distribution is going to be normal. Now that's incredibly important for us when we're out there making assumptions on polling data, manufacturing process data, supply chain time data. All of those, we have to, when we're doing tests, we rely on the fact that the averages are going to be normal regardless of the underlying distribution. It's a very powerful thing that we rely on. It's called the central limit theorem. And as we move into hypothesis testing, one of the assumptions we'll do is that we'll rely on the central limit theorem. Thanks.